Hello, from Dhaka, Bangladesh. This is the 14th lecture of A-level chemistry lecture series. In the 13th lecture, I end up with this slide, which was about the chemical reagents which can act as oxidizing agent and reducing agent in the same reaction, depending on the reaction media and temperature. Here we show a reagent which is hydrogen peroxide. When it is acting as oxidizing agent, it oxidizes iron 2 to iron 3. And you can notice that hydrogen peroxide here, oxygen has got an oxidation number -1. But after the reaction, oxygen gets oxidation number 2. That means this reagent itself is reducing. Though it's acting as oxidizing agent, but it itself is reducing. Similarly, we go for a reducing agent. You see, we have the same chemicals, but the reaction media is now alkali. And therefore, it is acting as a reducing agent. It reduces iron 3 to iron 2. And then you can see here oxygen is -1 and oxidation state -1. But after the reaction, the oxygen has got oxidation state 0. So itself, it is oxidizing. So then we go for the next lecture, 14th lecture. Here I'm talking about how to balance redox reaction. This is an important thing to balance redox reaction. So we have some steps to follow. First of all, we write the unbalanced reaction, redox reaction. For example, we are writing here, say copper oxide is reacting with ammonia, forming copper, nitrogen, and water. This is what is an unbalanced reaction. What we do to balance it, identify the oxidation number changes, how the oxidation number is being changed. In this case, copper is +2, it is changes to 0. Nitrogen here is -3, goes to 0. So we can look to this reaction and find out the oxidation number changes for copper and nitrogen. We can see oxidation number changes for copper is -2 and for nitrogen is +3. We have to balance these changes. So we multiply copper with 3 and nitrogen with 2. And then we will see that the oxidation number for this becomes -6 and oxidation number for nitrogen becomes +6. So this balances. And therefore we get, when multiply with 3 copper and 2 with nitrogen, we see this is the reaction, then balanced reaction. What we do, we balance the charge, we also balance the atom. You see, the copper here, there is no balancing in atoms, but here we have balanced atom 2. 3 coppers in the product side, also 3 copper, 2 nitrogen, product side also 2 nitrogen, and then we have 6 hydrogen and 3 oxygen. We can see there has 6 hydrogen and 3 oxygen. So this is how we balance using oxidation number changes method. Another example is here, how to balance this using oxidation number changes. This one was a compound reaction of chemicals compound, but here we have an ionic reaction. You see, manganate ion is reacting with ferrous ion in acidic media. This is what is acidic media. Whenever we get a hydrogen plus ion, we will say this is acidic media. And we see the changes in oxidation number there. The changes in oxidation number, manganese is +7 here, and here it is then +2. So there is a change, it's 5, -5 change in this oxidation number. Okay, we go for here, it's +2 for iron, and here +3 for iron. So there is a change, +1. So Now we have to balance this change of number. -5, we've reacted this with 5, multiply this with 5, and then this changes in a balancing is balanced. Therefore, we get this reaction now. Manganate ion plus 5 iron 2 and 8 hydrogen ion, manganese 2, iron 3, 5 iron 3, and water molecule. So we'll see that charges are balanced here. There's five charges, plus 5, and here also for plus 5 charges. So charges are balanced and number of atoms are balanced. It's 1 manganese, and then 5 iron, and then we have 4 oxygen here, so 4 water molecules. If you wonder how we showed this or how we find it out, please go to redox reaction first lecture. Redox reactions first lecture. When we started redox reaction first lecture, there we have everything about how we find out oxidation state, how we balance oxidation state number, how we balance charges that are given in the first lecture of redox reaction. Now we go for another method how to balance redox reaction. This is what we call half equations method. What does half mean? That you see that in every redox reaction we have an oxidation and reduction reaction going simultaneously. If we now divide this oxidation part or identify the oxidation part and reduction part and then make equation of this, we call oxidation half equation and reduction half equation. Using these two half equations, we can also balance redox reaction. And if you remember, we have been balancing redox reaction by changing oxidation number. Now we are balancing redox reaction by oxidation half equation and reduction half equation. Let's take an example. Here is sodium metal reacting with chlorine gas, getting sodium chloride solid, table salt. Okay, we find out in this reaction which part is oxidized and which one is reduced. So we can see sodium here is oxidation state 0. We said elemental form is always 0 oxidation state. This one, chlorine also, molecular chlorine has oxidation state 0. Now we go to the product and see the oxidation state. We'll see that we said group 1 element is always +1 oxidation state. Sodium is group 1 element. Therefore, it must be +1. And if we want sodium chloride, like neutral compound, chlorine must be -1, and then it becomes a neutral compound. So here, sodium has been oxidized to sodium plus ion, and chlorine, molecular chlorine, has been reduced to chloride ion. Okay, so we can write the oxidation half reaction like this. Sodium lost an electron and having oxidation plus, sodium plus, and the electron is here. We can alternatively write oxidation half reaction like this. Sodium minus an electron gives us a sodium ion. About reduction half equation, chlorine, molecular chlorine, if it gains 2 electrons, we get chloride ion. Now, we see if we want to balance redox reaction, we have to construct 2 half equations by balancing the number of electron gain and loss. And then we have to add these 2 half equations. Remember, we have to see that electron valence and gain are equal. and then add these two half equation and then see that the reaction, redox reaction has been balanced using half equation methods. Another example we can take, iron reacts with copper 2 ions in solution to form iron 2 ions and copper. So in this reaction, what you see, iron 2, copper 2 reacts with iron, metal iron, giving iron 2 ions, and copper itself get metallic copper. So oxidation half equation is metallic iron goes to iron 2 ion, and that is what is oxidation. It lost 2 electron. Reduction half equation, copper 2 ions gains these 2 electrons and get metallic copper. So these 2 electrons in oxidation half reaction and these 2 electrons in reduction half reaction cancels each other, and therefore we get this reaction. Copper, metallic iron, copper 2, and then iron 2, metallic copper. Now we have to balance the charge. You see here in right hand side, 2 plus, and also in the left hand side, 2 plus. Therefore, charge are balanced too. And this is the balanced oxidation reaction equation using half equation methods. Well, another example I'm taking, you might get question like this in your exam, that is an ionic reaction that iodide ion reacts with manganate ion in acidic media. Using this information, you have to balance the redox reaction using half equation method. So from this, we can see which one is oxidizing and which one is reducing, or otherwise we have to find out oxidation half equation and reduction half equation first. So manganate ion is an oxidizing agent. So this must be if we convert this one, it will be an oxidation half equation. So manganate ion in acidic media lose 5 electrons forming manganese 2 ion and water molecule. This is the oxidation half equation for this reaction. Well, we go for reduction half equation. If manganate ion oxidizes, then iodide ion must be reduced to molecular ion. So 2 iodide ion gaining 2 electron, getting iodine, and therefore this is a reduction half equation. So here we can see that we have 2 electron in the reduction half equation and 5 electron in the oxidation half equation. We have to balance this electron first. If we want to do so, we have to multiply this oxidation half equation by 2 and reduction half equation by 5. And then we have 10 electron here, 10 electron here. And doing so, we get this. What we get? 2 manganate ion, 16 hydrogen ion, and 10 iodide ion. And product is 2 manganate 2 plus, 5 molecular ion, and water molecules. You can now check the charges and find out whether the charges are balanced. You see, here we have 4 charge in the right-hand side, 4 charges, 4 plus. Here it is 10 minus, and then 8 minus, 2 minus, sorry, 10 are 2, but 12 minus, and here we have 16 plus. Then therefore we have 4 remaining plus charge. So then this will cancel each other, or balance, charges are balanced. So this is the balanced reaction of manganate ion and iodide ion. Manganate ion and iodide. This is the balanced reaction of manganate ion and iodide ion. which we are asking for. Now, there is another reaction in redox reaction. We call it disproportionation reaction. What it is, the same reactant will oxidize and reduce depending on the media and temperature. Well, in aqueous sodium hydroxide, if we add chlorine in it at a certain temperature, we will see that this chlorine is simultaneously oxidizing and reducing. The product becomes sodium chloride. Here you can see that chlorine is -1. So 0 to -1, that means it has been reduced. Okay, here in chlorine, if we get the oxidation number of chlorine, we'll say that it is plus, because this one is -2, sodium is +1, so this must be +1. So 0 to +1 and 0 to -1 for chlorine. Therefore, chlorine, both in this case, chlorine is simultaneously reducing as well as oxidizing. Well, we also find naming of inorganic compounds using oxidation number, how we name it. You see, there are traditional naming system in inorganic compounds as well as systematic naming system. Well, systematic naming system means that IUCN, International Union of Applied and Pure Chemistry, they have a nomenclature division. According to this division, everyone should name chemical compounds with their specific naming, and that was what is called systematic naming. But before this systematic naming was started, long before, well, people also name chemical compounds, and that is called traditional naming. Well, both traditional naming as well as systematic naming are in inorganic chemistry. But nowadays, for organic chemistry, one has to name all compounds using systematic naming. We are talking inorganic chemistry, so you see this example, copper sulfate. We call it copper sulfate or hydrated copper 2 sulfate in traditional name. But systematic name of this one is tetra-aqua copper 2 tetraoxosulfate 6 1 water. So many chemists prefer naming copper sulfate in traditional system than that of systematic name. Well, now also. So there are many oxides of nitrogen. Examples are this. These are all oxides of nitrogen. It is always preferable that naming of this sort of family of compounds to be done by systematic name. For example, here we do not say nitrogen oxide, we say nitrogen 1 oxide using the oxidant state of nitrogen. Yeah. If we go for this, nitrogen 2 oxide, we don't say monoxide, we say nitrogen 2 oxide. That is a systematic name. So in few cases, we prefer naming systematically, but in other few cases, we also use traditional naming in naming inorganic compounds. There are some examples of formula and also naming. With this, I finish this lecture. We'll continue this, and also in next lecture, we talk about states of matter. So thank you very much for today's lecture.